Okay, welcome to today's Blue Waters webinar. I'm Scott Lathrop with the Blue Waters Project at the National Center for Supercomputing Applications at the University of Illinois. Along with my colleague Maxim Belkin, it's a pleasure to welcome Magnus Strengert to give today's presentation. Magnus is a senior software engineer at NVIDIA and the technical lead for the compute kernel profiling tools. Magnus, it's a pleasure to have you here with us today, and we'll turn it over to you.
Thank you for the introduction, and welcome to the webinar about Nsight Compute. I want to jump in right at the beginning and start with an introduction in NVIDIA's Nsight Compute product family. Some of you might have seen the Nsight Systems webinar that was presented by Sneha a year ago. Nsight Systems is our starting point of profile analysis and optimizing your application. We have two other tools that I want to briefly mention today. It's Nsight Compute that we focus on today, and then we also have Nsight Graphics, which is geared towards analyzing any graphics applications. DX, OpenGL, Vulkan, all those things are handled there. A quick recap of Nsight Systems. Nsight Systems collects information from the CPU, the GPU, the driver, kernel information, and presents it all on one consistent timeline. So you see a lot of information all on one screen. And that allows to understand what your application and your whole system does over time. So it's low overhead data collection, and you then can see what happened over time on those various compute processors that you have in your system. It supports a lot of different APIs, has support for specific libraries. You can see in the screenshot there's specific rows for cuDNN, cuBLAS. The CUDA API calls are shown. You see when kernels are executed on the GPU. Some of you might be familiar with NVDP, our visual profiler. Nsight Systems is designed to scale to longer captures and larger data sets. So for the developers that listen in that have trouble kind of opening their reports in Visual Profiler, Nsight Systems is worth giving it a try and see if that scales better for you. So today we want to focus on Nsight Compute, and the idea would be you use Nsight Systems, run through a trace first, and then you identify areas in your code where a certain kernel doesn't behave the way you expected or doesn't perform as well as you would like it. And then you focus on that one kernel launch, forget all the other things around in your application, and jump into optimizing that one kernel. And for that, you switch tools from Nsight Systems then to Nsight Compute. And I quickly go through the features of Nsight Compute, and then we will have a look at a live kind of walkthrough through a report and discuss what you can see in those reports. So the idea of Nsight Compute is you collect performance information for a kernel in isolation. So you isolate a kernel, we collect as much information as we can do for that one single kernel to give you a deep dive into what that kernel does. And the report that comes up is that screenshot that you see here right now. It has a lot of sections that focus on various areas of the GPU, and it presents them all on one single page. Our previous tools like Nsight Visual Studio Edition, the Visual Profiler, NVProf, all those tools could show similar metrics, and the underlying mechanism to collect those are similar. The presentation is very different in the new tool, and hopefully you enjoy the way we present the data. It also has a access to the database of the tool that is a Python-based database, or the database is not. We have an API that allows to access it through Python. And we use that same interface to have a rules-based analysis on top of the report that helps you guiding through, or helps you as a guidance through the report, and gives you kind of hints for what we already detect as like performance pitfalls or common things that we see people do in their kernels. And we discuss that in a little bit more detailed when we do the live demo. You still see like familiar charts that you saw from the previous tools. Like for example, here would be the memory chart. That's the same chart that we showed in NVDP, as well as like the Visual Studio Edition. You see like all the data traffic between the various stages of the GPU, and get a really detailed view as like what your kernel actually transfers with memory. In addition, what's new in Nsight Compute is a typical workflow for optimizing a single kernel includes that you try a lot of different things, and you make changes, and you want to verify that your changes actually behave the way or achieve the changes you had in mind when you made your code changes. And for that, Nsight Compute has the concept of baselines within the tool. So you could come in the morning in the office, you make a snapshot, you make one of these reports, and then you can use that as a baseline in the tool and compare a later version of your algorithm or that kernel to that baseline. So what you see in the screenshot is suddenly everywhere where you previously would have had only one value per table, like cell, or one chart line, you now have like two, and you can compare like, oh, my version from the morning behaves like better or worse depending on the changes you did, and you can compare in which areas you kind of improved and in what other areas you might have made the code worse. And having that in the tool allows to have that workflow within the tool, so that you can see like making changes to code, what effect that has on the overall runtime of your kernel. We support multiple baselines, so you can even compare to many other versions of your kernel, and you can even compare across GPU architectures. So if you have a newer GPU and an older one, or you have to work on multiple machines with different GPUs in it, you can compare those as well and see like what part of your algorithm performs better on which chip. In addition, there is a new mode of creating these reports, what we call interactive profiling. The previous tools, like the command line tool NVProf, and also the Nsight Visual Studio Edition, you could select a certain kernel, and then you pre-selected like the name, and then it was running, and then it collected that data for that. So it was like a fire and forget kind of mechanism. And in Nsight Compute, we now have a method that with interactive profiling allows you to step API calls like you see in the screenshot. So you have full run control over which API calls get executed from all your threads in your application if you want to have that mode. And you can then kind of jump to a certain kernel launch that you have want to profile and profile it. So it's more interactive because you have full control over the runtime of your application. That works in some applications really well. In large scale kind of applications that you farm out into a larger cluster, we still support the other mode as well, where you can just pre-configure and have a command line tool that runs it and collects the data. We do support all the kind of features that you had in NVProf as well, like the CUDA start stop. In addition, you can now also use NVTX instrumentation. That's a small library from NVIDIA where you can do code annotations in your source code, and you can see you can see then the NVTX ranges in Nsight systems on the timeline. But in Nsight Compute, you can use those ranges and say only profile when you are in a certain NVTX range, or if the stack of NVTX ranges looks a certain way. So that's a quick way of also tracking down which kernels you want to profile. We still have the source code view that we had in previous tools as well. So some of you might know a similar view from the Visual Profiler tool. that's fully embedded in Nsight Compute 2. We do have a few more metrics in the new tools, like a lot more sampling data that you see on the left side. In general, the source code view, for people that are not familiar with it, allows you to even get performance data on a per source code line. So a lot of the metrics we collect that you see on the main page of the report are collected at runtime of the kernel, and they give you a good overview of what happened in your kernel, but it's an aggregate of the behavior of the whole kernel execution. While in the source code view, you can solve the problem of saying where in my code is a memory access that's not optimal. So it gives you a direct way of kind of jumping into the source code directly and finding, like in larger source bases that run on the GPU, it's quite important that it's not just like saying you might have some bad memory accesses, but it also helps you kind of finding where they are. Otherwise, you spend a lot of time tracking that down yourself. And in what you see in the screenshot here is that the pages can be correlated if you compile with line table information, which is like a flag for NVCC. You can correlate those two. So the blue background that you see, we clicked on a line in CUDA C on the left side, and on the right side, the lines that have blue background are all the SAS code, like the low-level assembly that is kind of attributed to that line. So that way it becomes a lot easier to understand like the assembly code, because you have that correlation and you can jump quickly between those views. Not many people want to read a lot of assembly code in that detail, but if you really want to kind of squeeze out the last percentages, then that's a really helpful tool. And sometimes it's just helpful to understand what the compiler made out of your high-level CUDA C code to understand what it actually executes. I mentioned already that all the screenshots I showed so far were all like UI based, and the UI is supported on Windows, Linux, and Mac. So it works on all of these OSs, and it looks exactly the same way. You can also open the report files that you created in one of these systems on any of the other OSs. But we still support also the same data collection and even the data representation on the command line. So if you only have SSH access to a machine, you can just run pretty much a command line tool. It prints the data either on the console or writes it to a file. And then from the file, you can either copy that back and look at it on your local machine, or you can print the data on the command line. Data collection is supported. Also, Linux, Windows, PowerPC is all supported. So you can collect on those machines. We even support remote profiling, where you can have the UI open locally, and you remotely connect to a different machine, and then it kind of executes the application on the remote machine, does all the data collection, and does all the file copy and transfer of the result data back to your UI. That might make your workflow even quicker. So that is all supported. Now I would like to switch to kind of actually run the tool. I hope that's visible on the screen. I have Nsight Compute open, and I have one report already loaded that was collected on the command line. You see that on the top we have a little header that pretty much says we are currently on the details page. If we would have collected for multiple processes, that is now in a single report. In Visual Profiler, you would have gotten multiple reports. In Nsight Compute, you can have all that data collected in a single report. And then we have another drop-down that is like just like the kernels that you collected that report for. So we could switch between those kernels, and you see the data in the bottom kind of switches. And now I just want to quickly go through a little bit of that report, how it looks like, and what you can see there. The first section, so we call one of these blocks that has like this expander and like that little header, we call that a section. The first section is called speed of light, which we use as a term for saying like how the percentage of peak performance you achieve. So it's like there is an absolute performance a certain chip can achieve, and then your speed of light values for the compute engines, for your memory subsystem, for L2 cache or DRAM. Those percentages here on the left, they tell you what percentage of that absolute performance the chip can deliver did you actually achieve. So it's a very high level overview of saying like in this specific kernel for kernel A here, it would tell you like this kernel is pretty much only busy doing some compute, but it doesn't do any memory. Because like memory percentage is like 1%, the other one is close to 100%. So it's a very derived example of saying like, hey, we are compute bound in this case. Top right gives you the basics of like how long did that kernel run, how many cycles did it take, what was the frequency of the chip it was running, and what was the memory frequency, so that when you make multiple runs and you compare them later, that you know that you actually run on the same chip or at the same conditions, and the values that you see are not influenced by like it was just cooler and your chip was running faster. And then from that high level view up there, you can jump into additional sections that give you a lot more detail on like what happens. So for example, for a compute bound kernel, we would jump probably to the compute workload analysis, open this up, and here you would see all the pipelines that exist on a GPU. This was running on a Titan V, and these are the actual pipelines that exist on that chip. And we can immediately see like the FP64 pipeline is the one that is close to 100% utilized. So all the other pipelines are pretty much unused. We pretty much fill up all of the double pipeline, and that application does mostly double executes double instructions. So that's currently the limiter here. If we could optimize our algorithm now to execute less double instructions or move some to a lower precision, that would kind of make that kernel faster, because we are limited by that pipeline. It cannot kind of make instructions look faster. Execute faster. So a little more interesting example to continue would be we look at an example where if you have a real world example, it will not be that easy that one pipeline is like at 100% and things are that easy. Usually you have a mixture of instructions, and you end up with something like this, where we go back to the top and you look at the speed of light section, and now the compute percentage of peak is not very high. It's like around 25%, and memory is also still pretty low. So there must be a different limiter that kind of holds back the application or the kernel to execute faster. And as you can already see below in the this is the rule output that I mentioned earlier. The system in the background run some rules, and wherever you see that little like sign, the warning sign, those rules detected something that you should put your focus on, or like might be of interest for you to kind of look at. In this case, it would say like both of these peak percentages are fairly low. So you should continue looking at two different sections, and one is called the scheduler statistics section or the warp state statistics section, because it may be like that we are latency limited. And if we open up these, so I just scroll down a little more. The first one it was telling me to look at is the scheduler statistics section. What that section is about is it looks at a single warp scheduler, and I have a few slides to explain what that unit is and what it's for. It pretty much tells the statistics of like what a warp scheduler did over time when we executed that kernel. In this specific case, we look at, was that scheduler busy, or were the warps that were assigned to that scheduler all kind of stalled and not making any forward progress? And this is what that chart is for, but it uses a few terms like theoretical, active, eligible, and issued warps that not everyone might be familiar with. So I quickly jump back to the slides. and explain those terms quickly. So on the Volta architecture, that is from the white paper that is published, and the warp scheduler pretty much is that little orange block up here. And that block here, as you see in an SM, exists 4 times. So in each SM, we have 4 warp schedulers in the Volta architecture. And each of these warp schedulers are independent from each other, and they manage a pool of warps. So when you execute your kernel, each of these warp schedulers get like a few warps assigned depending on the grid size you have. And there is a architecture limit. So in Volta, you can have 16 warps assigned to one warp scheduler, and on Turing it's 8. And the main performance kind of limiter there is like each warp scheduler is capable of issuing one instruction for 1 warp per cycle. So that would be kind of optimal if every warp scheduler issues 1 instruction per cycle. But that's not always possible, and we can look at like how this works with the mental model of the warp scheduler, how that works. So for simplicity, on the left side, I have these 8 warp slots. So we said Volta has 16, but for simplicity and for space on the slide, I just go with 8. It extends to 16 with the same algorithm. And then now we look at warps that we assign to those slots, and we can say if the little cell is white, it's completely unused. If it has a color, it's called active, because then a warp is actually allocated in that warp slot. And then we have 3 states to look at for an active warp. It could be either stalled, which means like it cannot make forward progress because it, for example, doesn't have its instruction loaded yet. Some dependencies are not read yet. The pipeline it once executed on is not ready. Things like this would kind of make a warp stalled and not capable of making forward progress. Warps that are not stalled are called eligible. Those are the pool of warps that could theoretically make forward progress because they have all their inputs ready and everything is prepared for issuing this instruction. And then we have a warp that is selected. And over time, we can look at this now. Let's assume we are in cycle n, and we have, in this case, like 5 active warps out of the 8. 3 of them are stalled. Those are the bottom 3. And 2 of them are eligible. The simple algorithm for the warp scheduler is it randomly picks one eligible and puts it in the issue slot. That's the one that makes forward progress on this cycle, on this warp scheduler. And then it continues on. So on that cycle, if we move to n+1, then this one warp might not be eligible anymore because it just issued. Let's assume like you issued an instruction that has a multiple cycles latency. Then that specific warp that issued in cycle n wouldn't be ready to issue in the following cycle. But we had another warp that was eligible, and then the warp scheduler would pick that one. If we continue in time, you could see like that some warps may exit. So then you end up with like that cell goes from issuing something to white. In this specific case, in cycle n+2, you would end up with a case where you only have 4 active warps. Those are the 4 at the bottom. And all 4 of them are stalled. That means the warp scheduler doesn't find any warp to make forward progress, and it misses to issue something. So you can just think like in this cycle, you just didn't issue a new instruction, and that possibility to issue was unused. As you move forward, then new warps could create. So like our active warps over time kind of is fluctuating. And then new warps might become eligible, and we pick one of these again and issue those. So this is how it works over time. And if we look at a few metrics that the tool can show just for those 4 cycles that we have on the slide now, we can already look at, we have 4 active cycles in our window of observation right now. When we count, I'm not sure if that's visible, if you count all colored boxes in those 4 cycles, those are 20, and there is a metric named warps active that pretty much does that for your kernel. So this pretty much counts every cycle how many active warps there were. So in our example, it was 20. And then we can already calculate a derived metric, which is like one out of those two metrics. If you divide warps active by cycles active, you get something that we call achieved occupancy. This is pretty much just saying how the percentage of active warps over time. In other words, like the colored cells in our example here versus the white ones. And this percentage gives you an indication of like how much or the percentage of how far you filled up the machine with warps. That's one way to say like what the achieved occupancy is. But we can do even more here. If you count only the stalled ones, like the darker green cells, that is 15 in our case here. This is like warp stalled. You can count the green ones, including the selected ones. Those were the eligible warps. This is 5 in our example. And we can also count how many were issued. Those were the striped ones. This is only 3 in our example. And out of here, we can then calculate what is called the issue slot utilization. That means the percentage of cycles in which you actually issue. And in our example here, we issued three times out of 4, so we are at 75%. And if you compare that now over a larger period of time, what we saw in kernel B was we had only on each cycle, like what I show here is like what we earlier saw in the report as kernel B. It executes double instructions, but we only have one active warp per warp scheduler. And then the image looks like this, that in cycle N, we issue an instruction, and then for 8 cycles, it doesn't do anything because we have no other warp that can do anything. And it takes 8 cycles for this instruction to issue. Then we ended up with like 7 cycles in between that didn't issue anything. Sorry. And if we compare that to the values in the report, sorry. If you compare that to the values in the report, we see that the values come out exactly the same. You see that warps active is 1, like we have from the excuse me, like what we have from the active warps active. Stalled is 7/8 pretty much because we only issue every or we have 7 out of 8 times is that warp stalled. 1 out of 8 times that warp is eligible, and in that one cycle it's also selected. So the values that come out in the report directly match to what we have in the report, and I can show you that quickly going back to the sample. This is in kernel B, and if you hover over these are the values rounded to 2 digits that you see in those charts. So if we look back to the chart, you see on the top is theoretical warps per scheduler. There you would see we could issue as many as 16 here on our GPU. Active, we only have that one that we just discussed in the sample. Out of that, the eligible would be only 1/8, and then the issued is also 1/8. So this chart pretty much is a quick way of understanding where do you lose kind of the ability to issue one warp per cycle. So if you have a lot of active warps, then the difference between active warps and eligible would be the stalled warps. So if you have a lot of stalls and a lot of dependencies, or you do a lot of memory instructions, and then you have a dependency right on the result of those memory loads, then you would see a big gap between active and eligible, and then you can see how many were issued. You can also see at the bottom that the rule system detected that problem and describes here in text what happened. Here it would say like every scheduler is capable of issuing one cycle, one instruction per cycle. But for this kernel, each scheduler only issues every 7.8 cycles, and then it goes on and explaining pretty much what we had on the slide. So it's a very quick way within the tool to kind of understand that problem and try to kind of do something. I quickly go back to kernel A, just as a difference for that one scheduler statistics section. And as you can see here, what changed is that we now have a lot more active warps, and those active warps allow for having more eligible warps, and then we end up with having an issued warp every quarter cycle. And I want to quickly explain that too, how we get to this values. In the same example that we had right now with the double instruction where we only had one warp, you can go back and say like, now we fill up the whole machine with warps that want to do a double instruction. And then on cycle N, all of them are eligible. Let's say like we start with a state where everyone is ready and could execute the double instruction. The warp scheduler will pick one of them and issue this one. That one warp now will be stalled for the next 7 cycles and can only reissue in cycle N+8. So I already kind of put that in at the bottom here. Then it continues, and in cycle N+1, N+2, and N+3, all remaining warps will be stalled because, as you can see on the right, the double pipeline has a dependent issue rate of 8 cycles, so that's why the bottom row is 8 long, and it has an issue rate of 4 cycles, so you can only issue to that pipeline any 4 cycles. So the N+1, N+2, and N+3 will not be able to issue anything. But in the 4th cycle, you will have all these other warps that didn't yet issue their instruction become eligible again. The warp scheduler will pick randomly one out of this place. Now this instruction or this warp will be stalled for the next 8, and I kind of make a wraparound. That's why the color on the leftmost changed as well. And then it continues with that pattern. And if we count here, you will see active warps is just like those 8 times 8, or in this case, I count the 8th one too. And then stalled active, the eligible warps would be 22 if you count the cells, and we issue 2. We calculate the metrics out of this, and you will see that for this, it also comes out exactly the way you see in the tool. I go back to the tool in a second, and the values kind of match to what you would expect. So I quickly change back. This is that example, and those values that you just saw on the slide are here in this tool now. And you can see that here we now issue double as much because we have more warps. So that scheduler statistics section is a really quick way of understanding, are your stalls causing you to not make forward progress or not issue enough work so that the GPU can be busy? If you want to understand why you lose so many kind of active warps and you don't have enough eligible warps, we can even look down here and you will see all stalls, the reasons for stalls over time. And this is the average of like how many cycles does a warp on average spend in each of these stalled reasons. Selected at the bottom is always at 1 because it takes 1 cycle to issue an instruction, and then you can see the relative size of like the other one. In this case, by no surprise, it would be the math pipe throttle. That means like you cannot issue more math instructions because the pipeline is so busy, is the highest reason why you kind of have so many stalls, because we only do double instructions in this example. So this kind of explains, like, if you want to understand where your stalls are, how to get to this. But I want to show a few more things in the report. So we already looked at speed of light, scheduler statistics, and warp state statistics. I quickly want to switch to kernel C, where this is an example where you are memory bound. So in this case, up here, going from the top again, GPU speed of light now shows the compute units are very low in peak performance, in achieving their peak performance. But memory is kind of the limiter. It's like at 85, 87%, I think here. So now the tool would recommend to look at your memory, kind of your patterns of memory instructions and what type of memory you are accessing. And for that, we could go down to the memory analysis. You saw a screenshot of this one already. The memory analysis section is kind of the deep dive into the memory subsystem, where you can see like how much data is transferred. On the left is your kernel in green. The next row of boxes are the different memory spaces: global, local, texture, surface memory, and shared memory. And then the blue ones on the right are the physical kind of caches that exist on the GPU. You have like the level 1 unified cache that is split between a cache and shared memory. And you have behind that an L2 cache that then can access like device memory or system memory. And the links in between show you how much actual traffic you generated for this. And the percentages in the boxes would be the hit rates for those kernels. For that one kernel executing for those caches. It's important to note that for Nsight Compute, by default, we kind of start with cold caches. So we make sure that for reproducibility, it's useful that you would say you can always have the same starting condition for a kernel. So we kind of clear the caches before we get the profile data. That's different from what happened in NVProf and Nsight Visual Studio Edition. There, it wasn't. Not all caches were cleared, so that might cause differences in the numbers of the tool. In Nsight Compute, there is a flag where you can opt out of clearing the caches, which is very useful if you only collect a single metric and you can collect it in a single pass. Then you get like a value that is closer to what the truth is when you run the application without any instrumentation. But if you need to do kernel replay to collect all of these numbers that I showed to you, then clearing the caches is making the numbers a lot more stable and a lot more consistent. So in this case here, what I wanted to show is like there is a lot of detail with all these tables where you see for each kind of cache, like for example here for the unified cache, for each of the memory access that you make, you get a lot of data, like how many instructions you executed, how many requests were made, how close this is to peak performance, the hit rate for each of those, the requests from texture then to L2. So it's a lot of data, and I would like to quickly give you the mental model of the memory system as well. So I switch back to the slides and quickly make a recap of the Volta architecture's memory system, so that we know like what the bases are for that table data, or for the information in that table. On that slide, you see the same memory hierarchy, the SMs. Each SM has like that unified text L1 text unit, and then you have like one combined L2 and the FB. Like the frame buffer or kind of your global device memory at the bottom. On the right, I put it like the numbers of the sizes of these caches and the throughput. As you can see, like the closer you are to the SM, the faster you can read the data. The further down in that hierarchy you get, the more costly an access becomes. And for the unified cache, the cache is organized like with cache lines. They are 128 bytes in size, and they made up of like 4 sectors of 32 bytes. And the cache line itself is 128 byte aligned, so you can think of it like 4 of these sectors in one cache line, and then an access kind of is matched into those cache lines, and we read only the sectors we need. So it's like that is pretty much what's on this slide is saying. Like for memory reads, you start from the SM. You check in the L1 text cache if it's there. If yes, it returns the data quick. If not, it makes a request to L2, checks if it's there. If it's not there, it has to read it from the frame buffer. And the unit in which we move data there is a sector. So whenever you have to access a unique sector, then the whole sector is kind of transported. And for the reads, it's fairly similar. For the reads, it's technically sectors. Sometimes it can be less because there are partial writes, but it's the easiest to think about it in sectors. L1 is write through, so it writes to L1 and keeps the data there and informs L2 about it. L2 is write back, so it flushes the data back to FB when needed. And there are a lot of modifiers that allow to kind of influence the behavior from those caches. But if an actual access now, let's assume like you make an access, you have a full warp of 32 threads, and each warp wants to access 4 bytes of data, and they are perfectly coalesced, which means like each thread reads like the subsequent 4 bytes from the previous thread. Then the picture could look like this if you are perfectly aligned with the cache line at 128 bytes. And then you would see that you would read 4 sectors per instruction that you issue. So that warp issues a load instruction. You would kind of calculate it needs data from these 4 sectors, and then these 4 sectors get read. In the table that I just showed you in the tool, you can see that by the number of instructions and the number of like returns you get from L2, if you make the ratio between them, if you have an access like this, the ratio would be 4, which is for this 4-byte access and all threads active would be an optimal kind of way if you want to read a pattern like this. And now we just go through a few more patterns that allow to kind of see what changes in the table, in the tool, and also in the memory access. So if all read the same value, so you have 32 threads, we didn't change anything there, it's still a 4-byte access, but now you have a 0 bytes write, so it means like everyone reads exactly the same data, then it's like you only have to read one 32-byte sector for each of the threads, and then the number of instructions at the bottom in the table, the number of instructions you execute and the number of like sector returns you will see is exactly the same. And this behaves the same for the reads and the writes. So I always show it twice on the bottom. The top is for the reads. So this is global loads that we read in, and then we do the same access pattern for the global stores. And you see that's a one-to-one pattern there too. A little more interesting is like something like this. If you again have a full warp 4-byte access and you would stride it in a way that each of these accesses, like each thread needs to access a unique 32-byte sector, then you need to return 32 times the data that you actually wanted to read. And I wanted to kind of stress that example is like, in total, the warp only wants to read 32 times 4 bytes. So in total, the kernel asks for 128 bytes, but what actually gets transferred internally would be 1K bytes from L2 to back to L1, because it needs to read all these sectors. So you see that the tool immediately shows you kind of what your access pattern is, that ratio between instructions and these sector returns. Clearly shows you like how efficient your access pattern is, and it is it matches to kind of that mental model on the top for how those accesses work. In the real world, it's a little more difficult than what I show here on the slides, because sometimes you have like a warp that doesn't execute all 32 threads. Sometimes you read the same value and you get an aggregate from all of this in that table. So if you see like a factor of like, let's say, your instructions and returns would be a factor of like 1 to 6 or something, then it still doesn't mean like that you are fairly close to like the times 4 that I said earlier that is pretty optimal. Because if you only execute half warps, then you might want to be only maybe more at times 2 at this ratio. So it's very dependent on like how many threads are active in a warp when you execute those memory instructions, what the pattern is, and the alignment of your data is important too. So I want to quickly switch back to this. So the table that I had on the chart was this table here. It continues the same way with the L2 table down here. So again, you can see like the incoming requests from the L1 cache, and then you can see also here the cache hit rate, and then ultimately down here you would see how much data was actually requested from the device memory. And so it's a lot of data, but like if you go through hierarchically and kind of make your way through that report, it can help a lot to kind of understand what your kernel is doing. I also mentioned upfront that if you would like to understand now where your accesses are in the source code, you could switch to the source. And I just want to kind of highlight this quickly of like what we see is on the left side, you have your CUDA C code, and it's a fairly simple kind of kernel that is kernel C, just calculates that stride at index and does like a vector addition. And on the right side, you see the simple kind of SAS code, like the low-level SAS instruction. And as I click on the left side, you see that this right side, the background kind of changes. So I just do that again so that you can see it better. These are the underlying SAS instructions that are correlated to the line I click on the left. So if you click on like that one line that actually does the calculation, you would see on the right side, you have like here an LDG, which is like a global load. You have the store in here. We have only one global load here because you see down here is like this is kind of read twice. So in this case, it's only one global load, one store, and you have like that double add in between here too. So it's fairly kind of quick to understand for that one line is like what the compiler made out of it if you want to go to that detail. But it also allows you on the high level, so I scroll a little to the right here, you see is like we have sampling data in here, we have the next columns will be how often an instruction was executed for this high level lines, how many threads executed the instruction, and then we do have also like here this is a success to global, we have a load and a store on this line, and they are 64-bit wide, and you would see like how many global transactions you created in L2 for this. That way, assume like you have a lot of them in your application and you want to find the ones that have a lot of transactions in L2, you could quickly sort that column by just that value and find like the few memory kind of loads and stores that don't behave perfectly or don't behave as good as you would like it. What's maybe also interesting to show for this one here, the sampling columns are, it's a sampling profiler. So what we do is we execute your kernel, and while it executes every n cycles, we collect sampling information that includes where is each warp scheduler at that time, and what is the state of the warps of that at that cycle. So what happens technically is like you can hover over this line and see how often this line was active at a warp scheduler, and you get the same stall reasons we discussed earlier per source line. So in this case, you would see like that this one line is the one with the larger stalls. So if I unselect this one, you see like this is the one line that has all the stalls. And if I hover over again, you will see the stall itself that has the highest percentage of these is the what's called long scoreboard. This is how we keep track of outstanding memory instructions. So you made a load and you want to do the addition. So on the right side, you can see this. If I click on this, we made the load here. It stores its value in R2. And then there is the double instruction down here that wants to add R2 to R2 and saves it out to a different register. And this instruction kind of needs to wait until that load comes back. And the load, as we discussed, goes now and makes that request to the first unified cache. If it's there, it would come back quick. If it's not there, it goes to L2. If it's not there, it goes to DRAM and loads the data back. And the double addition has to wait until that data becomes available, and that wait is kind of captured with that with those stalls in here. So the same discussion that we had for the warp scheduler statistics section, you can even have that with the sampling data on a per source code line. And you see that it kind of matches you for people that only want to see the source code on the left. It kind of maintains this for this one line, creates a lot of like stalls because of using the dependency of the load immediately. If you would have more instructions that the compiler can put between the load and the actual addition, then you could like stretch that out, and you wouldn't. You could all execute those independent instructions in between there. If you make that dependent instruction right after the load, then you will see those stalls here. And you also kind of see that this is quickly to kind of understand that in the low-level code. The difference between the two columns, like there's a sampling data all and sampling data no issued, is the sampling data all takes all samples we can collect. So every n cycle we collect the data. The sampling data no issued discards the samples on cycles where you actually issued. The idea behind that is that stalls on cycles where you issued are not really a problem, because you were able to hide the latency by taking a different work and executing that. The cycles where you didn't issue are the ones where you would like to fill it up, as mentioned earlier in the discussion of the warp scheduler. And if you only look at those samples, those are pretty much the stall reasons you should try to reduce, because those are really causing what we call like an issue slot miss. So it's a quick way of like in large code base to kind of find out where you might have sections of code that have create a lot of like stalls. Okay, then I want to quickly mention up here, I switched between the details page, which was like the main part that we discussed. We also looked at the source page. There is a lot of other things in here that I just want to quickly mention. The session page just collects like base information of where do you collect everything and what was the parameters of the application you were collecting. Summary page has an overview of all the kernels. Let's assume like you run this profiler on like, you know, many kernels in your application, then this page would fill up. We don't recommend that you collect, you know, it's like a blind kind of every kernel in your application with Nsight Compute, because data collection can become fairly slow if you collect the whole report. We would rather recommend using Nsight systems at that point and first do a run there and identify the kernels of interest in Nsight systems and then jump back to compute. But you can have multiples in here and quickly compare them. You can even add comments to each of the sections or the whole report, so that when you send it to a coworker of yours, you can kind of keep track of things in here. You can, if there would be NVTX instrumentation, you would see the state of NVTX at the time of getting the profile, and the raw page is a way of looking at all metrics. So if I do that, this is all the metrics that were collected for this report for all three of the kernels we have in this report. So this is a quick way of comparing and getting the raw metrics out as well. All of this can be either kind of saved as image, as PDF, can be exported as SVG if you want to kind of do your own analysis on top of this. And I also mentioned at the beginning already, all of this in the details page is technically data-driven. So they are text files on disk that you can modify and kind of add your own sections here if you want to focus on something else that we didn't implement yet or is not part of the default set. You can change all of this. They are in clear text, so you can even see how we implemented them. The same is true for the rules. They are written in Python and are shipped as Python files alongside the tool. If you want to add your own to kind of say like this kernel should never be slower than a certain kind of number of cycles, then you could kind of put that as a rule in there, and every teammate that makes changes to it would see your warning there. Things like that. It's very customizable for the users that want to make use of that. Obviously, we say like we ship with a reasonable set of rules and section files, but some teams want to always extend it and have their own things in there too. So I switch quickly back to the presentation. I just have like a quick slide at the end. Yeah, now it's there. The main web page is just developer.nvidia.com Nsight Compute. It's available freely, and if you never heard of it before, you might actually have it installed on your system already because it's part of the CUDA toolkit. if you have a toolkit that's, I think we started shipping it with CUDA 10.0. So if you are on a 10.0 or any newer toolkit, you have Nsight Compute on your system already. You can also download it separate from the toolkit and just like unzip or install it on your local account through the register program, the register developer program, and documentation is installed locally, or you can get to the latest on the web as well. That's all that I wanted to show. Thank you for your attention. I hope that was useful, and if you have any questions or comments, feedback, or things you want to see in the future, let us know. We are happy to take your feedback. Thank you.
Well, thank you, Magnus. That was an excellent overview of the Nsight capabilities, and clearly the tool is evolving considerably. For the viewers, if you have questions, either post them to the YouTube chat or to the Slack channel if you're connected there. In the meantime, we have a couple of questions for you. One is, you have a good pointer to the documentation. Are there training resources available to help people learn how to use the tool as well?
Yes, there is. The documentation consists of multiple sections. I think one to point out would be we have a transition guide for people that are used to use NVProf or a visual profiler. For those people, we have a specific part of the documentation that contains like the changes in metric names and changes in command line parameters to make that transition as easy as possible. There is a recent parallel for all blog posts that also kind of goes through a full analysis of like a kernel with Nsight Compute, which is a good resource to kind of see an example how Nsight Compute was used to optimize a kernel. And the last two GDCs, we had like another kind of talk. GDC 18 was like the first time we showed Nsight Compute and gave like a quick overview of the capabilities of the tool. And in 19, I had a talk there for going through an example of like how to optimize the code. Some of that warp scheduler work is discussed there too. So that would be the best training resources, I guess.
Very good. I think Maxim has a couple of questions.
Yes, first of all, thank you, Magnus. It's indeed very interesting presentation. So my first question is, you sort of answered this question on your last slide when you mentioned CUDA 10, but in general, I assume that your tool runs on the latest GPUs, but what are the oldest GPUs that it can run on?
Nsight Compute currently starts from the GP10X cards. Those are Pascal-based cards, so you can run Nsight Compute on those cards and everything newer. So it's like GP10X Pascal cards, Volta, and Turing cards. As you already mentioned, like the visual profiler in NVProf is not gone yet, so the current toolkits are still there, and we ship them, and they cover like the previous tools like Maxwell architectures up to Volta. So when you are on a Volta architecture, you are in the nice spot of being able to use both tools, and that was on purpose so that people have one architecture to kind of transition from the one tools, like from the existing tools, to the new tool chain that we have, so that you can compare the tools, but also kind of change your workflow and prepare yourself for like using the new tools from there on.
All right, thank you. And my second question is related to the first one. So because it can run on several generations of NVIDIA GPUs, how do specifics of GPUs, hardware specifics like compute capabilities or number of threads and so on, affect the recommendations that the tool provides?
Yeah, that's an excellent question. The capabilities of what we can collect are slightly different between the chips. So you will see when you collect the report that some of the more detailed sections that we have would only be available like on for example, a Volta card and newer, but not yet on those Pascal cards, even if you run the same tool on them. So some data is simply not available because it wasn't possible to collect that data on previous cards. So an example for that would be the sampling data is only available for Volta and newer because that's when we could expose that data. In terms of like the chip itself influencing the data, for a lot of the metrics we defined in the new tools, we try to kind of avoid that this influences you too much. So for example, the speed of light section operates in percentage of peak performance, which is a nice way of looking at things because it kind of divides out the chip specifics. So if you reach 80% on a certain chip, that chip could be a high-end card and you reach 80%, or it could be a low-end card and you reach 80%, but the chip specifics are kind of taken out. So the metrics in many cases in the new tools were carefully designed that it's at least like comparable between chips. Because if you would see the raw value of like you made this many instructions per cycle, that could be fairly different and includes like how many SMs you have and how large your kernel is. But the percentage of peak or like the SOL value is a little independent of that. And we do that across the report so that you always get an impression on like this is a value that is worth comparing cross chip or cross even with one architecture from a high end to a low end card. It's not capable to kind of remove that completely from the tool because at some point you want to be very architecture specific and very specific on your one chip. So we still have at the bottom of the report like the occupancy sections that kind of help you there to understand. We have a metric that is called like waves per SM, which shows the grid size in relation to how large your GPU is, like how many compute resources you have. Because if you have a certain grid size and it's a fixed grid size and you run it on a high-end chip, it might not even fill up the whole machine. And then you run it on a mobile chip and it takes like multiple, what we call waves, like multiple theoretical kind of waves of data that go through sequentially then to execute the whole grid. So some metrics are very chip specific and some are not. But yeah, I hope the new metrics in the new report are a little more clear and detailed on like what is comparable and what's not. I hope that helped.
Yes, thank you. So actually, I just came up with another question. So basically, your tool allows to optimize for a specific GPU. Is there a way, or maybe a suggestion, how to avoid over-optimizing for, like optimizing for NVIDIA GPUs, but still not over-optimizing for specific architecture or something other, like general recommendations section or something like that?
Yeah, it is a common problem. I would say that if you optimize too deeply for only one chip, then you could result in making other chips even in the same architecture like high end to low end less efficient. Some optimizations like fixing your memory access patterns are uniformly kind of helpful if that architecture from high end to low end works the same way. Identifying that you are like latency limited or something is usually also something that is like helpful across the board. The more advanced your optimizations get, once you get into like that source code and SAS code and kind of try to make more changes there, the more kind of specific it becomes for your one chip. In general, we kind of would recommend that even if you optimize a single kernel, that you, after your optimization routine, always go back to Nsight systems and make a quick run there again, because even if you see a large gain in Nsight Compute in a kernel in isolation and you would go back to Nsight systems, if you weren't on the critical path, your application will not be quicker. Or another example is if two kernels were running in parallel in Nsight systems, but you only profiled that one in Nsight Compute, you made it faster, but at the cost of like now using the GPU to 100%, then that kernel in parallel will not make progress and you might make your whole application slower. So the workflow that we recommend is kind of a loop between Nsight systems, understanding that you actually use your available resources well, and then if you identify that you are GPU bound and a kernel is not performing the way you want on that specific chip or on that hardware, then you jump in, make it faster, and go back to kind of see if the overall was better. So that loop between trace and profile within the two tools is still important. So it's like your work is not done if your kernel is like perfect in Nsight Compute. You should go back to that step and do another run in Nsight systems as well to verify that it actually made your application perform better.
All right, thank you very much. Excellent pitch for Nsight systems.
Yeah, the tools work kind of together. You know, it's like the idea of having them under that Nsight umbrella is not like that we had the two tools. It's like we face the same problems when we optimize code ourselves, and there the tools work together. So it's like it is important, I think, to kind of understand first that improving a certain kernel has an effect. If that's not the case, then you can still run Nsight Compute, and it's maybe a fun exercise to go through and make it faster. But if you really are interested in making your application faster, I think both are there for helping you. So yeah, and I mentioned it earlier in the talk. It's like there is the same. We had a webinar, I think, nearly exactly a year ago for Nsight Systems as well. So if you're not familiar with that tool, look at Sneha's webinar there, and then hopefully both webinars help you to get performance of your application too.
Thank you very much. Thank you.
Okay, with that then, I want to thank Magnus for a great presentation. We appreciate your time and effort that went into this. At this point, we do not have any more webinars scheduled, but if you are registered for the webinar series, we'll let you know if and when the next session is scheduled. With that, we thank you for joining today, and we hope to see you again in the future.